Hello everyone. In this video, we are going to talk about thread tolerance, an important topic for you if you want to do anything that needs screws, bolts, anything like that, fasteners. So just before we start, some text here is taken from this website, which is a good website for learning about these topics, but mainly they are basically manufacturers of connectors and fasteners, but they have some material on their website too, which is useful. So like anything else that we manufacture, threads, they also have tolerances. And a high or large tolerance or loose tolerance means that, of course, the fastener could be general use. If it's a low or tight tolerance or small tolerance, that means it's for specialized use that needs high accuracy, high precision, like advanced aerospace industry. So we should not really use a very tight tolerance on fasteners that are not for a specific use. And if they are, we should not use a loose tolerance. So how do we show tolerances on threads, and how do we know how to read them and how to decide? So here we're going to look at metric threads first, and then we're going to talk a little bit about the UN threads as well, okay, or UTS you might call them. So the metric threads, as you remember, when you want to show a metric thread, the way you show it is you show the letter M followed by the major diameter and then times and then the pitch. Okay, so these are this is the common way to show a metric thread. But if you looked at many times that you use SolidWorks or anything and use the whole callout command or other commands, you see that right after that there is dash, and then there are one or two letters that are about the tolerance of the thread. So let's see what they are, what is it that they are, how to interpret them, how to quantify them, and so on. So if you remember, each thread has a minor diameter, which is the distance between the root and the root of the thread. It has a major diameter, which is between the crest and crest of the thread, and it has a pitch diameter, which is between these two. And the pitch diameter is defined as the diameter at which the thickness of the thread is the same as the space between the threads. So at that diameter, we call it pitch diameter. These two are equal, okay? So if the major diameter is D, how do we find minor and pitch diameters? Well, for standard threads where this angle is about 60, not about exactly 60 degrees, and pitch is P, then the minor diameter can come from this formula, major minus 1.22687 P, and the pitch diameter is this guy here. And so these are the formulas for pitch and minor in terms of major and the pitch itself. Okay, so because we need to know them for the example that I'm about to show you, we need to know how to calculate these numbers. Okay, now going back to the metric. So the way we show the metric thread needs two pieces of information. One is what we call the tolerance position, which is shown by a letter, okay? And that shows basically the offset, that shows the deviation, the basic deviation, fundamental deviation, or the location of what we call tolerance zone with respect to the thread nominal size. That is called the tolerance position. The other one is called the tolerance grade or class, a number which determines the size of the tolerance zone. So one is the location, the other one is the size of the tolerance zone, and the size, of course, determines the precision with which you have to make the thread, okay? So if you can see here, as I said, there is a number like 5 or 6, and there is a letter like G. So G is the location, 5 or 6 is the size. Now, what is the meaning of them? Let's talk about that. So the numbers or the tolerance grade, the numbers are anywhere between 3 to 9, okay? The bigger the number, the looser the tolerance. So class 9 is the looser tolerance, the cheapest one to make. Class 3 is the tightest one to make, okay? That's one thing. Two, depending on whether the thread is an internal thread or external thread, And whether it's for internal, external, whether it's pitch diameter or whether it's minor or major diameter, there are only different classes that are allowed. So for instance, if I want to put tolerance on external thread pitch diameter, I can use all of the classes. But if I want to do that for major diameter of external thread, all I'm allowed to use are classes 4, 6, and 8. For internals, minor diameter is 4 to 8, and also for pitch is also 4 to 8. So I cannot use classes 3 and 9 for internal threads. Okay? So this is one thing that we need to talk about. So one thing we have to do is to break down the discussion into whether it's an internal thread or external. We have to separate how we show tolerances on them, and that is what we're going to do in the rest of this video. And then of course, as you see here, we have to be able to calculate the minor diameter and calculate the pitch diameter, for which I just gave you the formulas. Okay, so this is about the class, correct? And the other thing is now about the leather. That's leather. What leather is that? So as we'll see, for internal threads, the only two letters that are allowed for the location are capital G and capital H. Where capital H means no deviation from the nominal value, G means positive deviation. What is positive deviation? Positive means bigger than the nominal size. And you know that an internal thread should always be equal or bigger than the basic dimension. You can never make an internal thread less than nominal size. Otherwise, that male thread will never pass through, okay? So it has to be bigger than or equal. It has to be 0 or positive deviation. And that's what it is. G is positive, H is no deviation. Okay, so these are for metric internal threads, and you see they are using capital letters for internals. On the other hand, for externals, we use small letters, A to H, so there are 8 classes as opposed to 2. Again, the small h means no deviation, A to G means some deviation, but these deviations are all negative deviations. And of course, you know that an external thread should be equal or less than the nominal size. Otherwise, it can never be used with an internal thread. It cannot basically be tightened through it. And as you go from A to G, the deviation is basically reduced. So A has the biggest deviation from the nominal. G has the closest to almost none. Okay, so as you go from A to H, it is going from negative numbers all the way to 0. Right? So far, we learned what each letter means for external or internal, and what is the meaning of each basically class. So 3 to 9 means increase in the tolerance, size of the tolerance zone, and anywhere from A to H or G to H means reduction in deviation of the tolerance zone. Okay, so far. Now, how much are they? What is the number for G, H, 1, 2, 3? I'm going to show you the tables for that. We're going to see the tables. But first, let's see how we are going to show the internal and external thread tolerances differently. So if you look here, we can see that for internal threads, the way we show it is after the dash, we show one tolerance for the pitch diameter followed by another tolerance for the minor diameter. By the way, these two red and blue squares are the things I added. You never have those squares, okay? But if you show 5G, 6G, what does it mean? It means the pitch diameter, if you want to inspect it, if you want to measure it, you have to use class 5G for inspection. For the minor diameter of the internal, which is the smaller one, you have to use the class 6G. On the other hand, if it's an external thread, the first number is again pitch diameter, so pitch diameter of external is 4G in this case, but the major diameter of it is class 6G. So pitch and major for external, pitch and minor for internal. These are the things that you can inspect. And of course, that's the case because For an internal thread, really, measurement of the major diameter is not something you can easily do, but the minor diameter you can do by a caliper easily. The same thing for externals. For externals, basically measuring the external diameter is something you can do with the caliper easily, but internal is not as easy. Okay? What about pitch? Pitch is an imaginary circle. Pitch is not a physical circle. So how would you possibly inspect the pitch circle diameter? For that, there are different methods in the literature, and one method that is common is using 3 standard wires with specific diameters, and that I will cover in a separate video, okay? Because that needs a video of its own to talk about how you inspect the pitch diameter. But internal and external minor for internal and major for external, you know how to easily use a caliper or micrometer, internal or external micrometer to do that. Okay, so we'll talk about that topic separately. So this is how you show it. Now, one other thing before I move on to the tables I have to mention is if the 2 classes for the pitch and the major or minor diameter are the same, then you are not going to repeat the symbol. What does that mean? Means if in this case both of these guys, or in this case let's say this minor, remember we can go for both of them, we can go anywhere from 4 to 8. So if both of them are 5G for this minor diameter, I'm not going to show 5G. I only show that 5G once. So if you see something like M10 times 1.5-5G, what does it mean? Means for internal, it is for minor diameter is 5G. Also for pitch diameter is 5G. They are both the same. I'm not going to show it twice. The same thing here. Remember the pitch one, if you just go back and look, the pitch can go anywhere from 3 to 9. The external one goes 4, 6, 8. So let's say both of them are 6. So if both of them are 6G, again, I'm not going to show 6G. I'm just going to show that 6G once. So if you see it once, that means they are the same thing. Okay, so that's another topic that you have to pay attention to. Now let's look at the numerical numbers for these different classes and different locations of the tolerance zone. What do they mean mathematically or numerically? For that, you need to get these tables called the ISO 965, 1, 2, and other tables. These are the important tables that can give you those numbers. For instance, here, this first table is about those locations, A, B, C, D, all those letters. So here, if you look, for instance, for an internal thread and then location G, if the pitch is 1.5, you go down and you find 1.5, and you see for 1.5, the amount of basically displacement from the nominal size is plus 32. Okay, so if it was this example that we did, 5G or 6G, let's work on this example here. Let's say this is what we have. So for both 5G and 6G, it doesn't care 5 or 6. As long as it's G, it's a positive 0.32 micron, right? 32 microns. So in terms of millimeters, because these dimensions are all in mils, that capital G is plus 0.032 mils or 32 microns. That is class G. So both of those dimensions, whether it's minor diameter or pitch diameter, they are 32,000 bigger than their own nominal dimension. How much are their nominal dimension? We have to calculate it with these formulas. So in this case, if we want to know the minor diameter here, that's minor diameter, major is 10 in this case, and the pitch is 1.5, and similarly here, 10 and 1.5. So if we use these formulas, we should be able to find minor and pitch diameter for the 10 by 1.5 thread. So let's calculate it. So these are the numbers we find using calculator. Now, the thing is this. If you look at our tolerance is only basically up to what? It is up to 3 decimals, right? Remember, we said that class G means, let's show it here. Class G means 0.32 or 32,000 of mils. So here, these numbers are up to 6 decimals after mil. We are not going to use that. We are going to only round it to 3. So here, we get rid of these and round this to 160. And the same thing here, we're going to round this to 0.9.026. So in this case, if we want to get them, the minor diameter is 8.160, and that is 9.026. So these are the nominal dimensions for pitch and minor of this kind of thread. Now, class G means each one of them should be added to them 32 thous because they are class G. Okay? Now, what does 5 and 6 mean? So let's go and see what 5 and 6 mean. So that was just class G. So right now, what we need to do is to add a 32 offset to them. Remember that internal threads are always bigger than or equal. So we have to add this number to them, not subtract it. So that is for internals, and also for externals. If you want to do it for the other example, for this one here, again, we go to class small g, and for class small g again, you see that if you continue this here, if you continue this 1.5, let me click outside here. If you go down here for class G, you see it's negative 32. So negative 32 thous should be added for class small g in this case. And of course, if you want to do it for this one as well, so let's do it at the same time for these. In this case, major diameter is of course 10, and pitch was, if you remember, 9.026. So in this case, you should subtract a 0.32 from both of them, because G means negative 32 micrometers. Okay, so far these are the dimensions, the basic deviations. Now we have to get those pluses and minuses. Okay, the tolerance size. That is where we have to go to those tables. So for each one of those, there is a separate table. So for minor diameter of internal, there is one. For major diameter of external, there is one. And if you go down for pitch diameter of internal and external, there is one. So now let's work on these examples. So here, if you look for the internal thread, we have class 5 for pitch and 6 for minor. So 6 minor and 5 pitch. So let's go down for minor. Remember, it was class 6. It was 5G, 6G. So 6, if you remember again, look, 6 is for minor. So we're going to use class 6. And for class 6, which is right here, we are going to have the pitch of 1.5. So it's here, and pitch of 1.5 is here. And if we go down, the number you will get is 300 microns. So 300 is for a minor. Then if we go down for pitch was class 5. And here you need to know the major diameter range and the pitch. So the major is 10, which is between 5.6 and 11.2. So it's here. The pitch is 1.5. So we're going to follow this and 5, and we're going to get 140. So 300 for minor, 140 for pitch. So if we come back here, then this is going to be plus and minus 300. And this is going to be plus and minus 140. Done. So first you add these two numbers together, and then plus minus that is the tolerance for the pitch. Then you add these two numbers together, plus minus 300. That is the number for minor diameter of this internal thread. Now, if you want to do it for this external one, pitch is 4, major is 6. So we go to major 6, class 6, that is major, pitch is 1.5. Again, we go down. You see the number is 236. And then for pitch, it was class 4. So we go down class 4. Again, diameter falls in this range, and that is the pitch. So we follow that, we follow the 4, and we get 85. So 236 and 85. So this is going to be plus minus 236. And this is going to be plus minus of 85,000. So again, you subtract these two plus minus that for major, and subtract these two plus minus that number. That is for what? That is for pitch diameter. Okay, so now hopefully you see with ISO 965 tables and with these classes and the tolerance locations, you can easily read and interpret the thread tolerance. Now, with all that in mind, the next question that comes in is, what class of tolerance do we pick, right? So we have different classes, tighter one, shorter, basically looser one, different locations and so on. Which one should we pick? Now for that, here there are some recommendations. It said grade 6, which is somewhere in between the very tight and very loose, is used for tolerance quality medium and normal length of thread engagement. What is length of thread engagement? I'll show you in a second. But if it's a normal thread engagement length and medium quality, go for class 6 or grade 6. Below 6 are for tolerances that are quality or the length of thread engagement is short. Above 6 are for loose quality, coarse quality, or when you have a long length of thread engagement. Okay, so the class that they typically recommend for an internal thread is 6H, which is the average. This is no deviation, and this is medium quality. And for externals, they go with 6G, which is basically, again, medium quality and very, very bare minimum deviation. Very slightly smaller than the actual size, so they make sure they always go together. But there are combinations here that you can see. And as you just learned, one important factor in deciding that is the length of thread engagement. Now, length of thread engagement, what is it? And it has 3 classes: short, normal, and long. Let's briefly look at that, what that one is. So the length of thread engagement is the distance between the threads of a bolt and the threads of a knot, or a male and a female thread, when bolt is fully screwed in it. So here, if you look, when this bolt is gone inside this internal thread, the portion that the threads are engaged, that is the length of the thread. Now, if a bolt passes through a knot, of course, only inside the knot the 2 female and male threads are engaged. So only the size of the knot, the height of the knot, will be the length of the thread engagement. So only the portion of the thread that the 2 have contact with each other. And the way we basically specify that, we typically specify it as a multiple of pitch. So if we say the length of thread engagement is 5P, what does it mean? It means only 5 of these threads, 1, 2, 3, 4, and 5. Now in this case, you see it's 6, 7, 8, and 9. So this case is a 9P length engagement. If there are 5 of them, there it would be 5. Now, of course, in this case, yes, 1, 2, 3, 4, 5, 6, 7, 8. It's 8, not 9. A pitch is the distance between each one and the next. So this is like an 8P engagement. And there are classes of short, normal, and long, of course. If they are very small, connections, normal connections, or long connections. Now, here, let's take a look and see what is each class length of thread engagement for metric threads. How is it determined? So here you look at the basic diameter or major diameter. So for instance, for M10, which is, it was here, and for 1.5, you can see that if S is up to and including 5P, basically it means that is a short one. If it's anywhere between 5 to 15 of the threads or pitches, that is a normal one. Over 15, that is what? That is basically, let me use less than, and this is like this. Then we can call it a long. So you have to see how many threads, how many pitches is the engagement in your scenario, and that will determine whether it's short, normal, or long. Now, when you determine that through this table of ISO 965, now you come back here and take a look. Now, let's say for your application, the quality is important, so you care about the fine or tight tolerance, and the basically thread engagement is very short. Okay, so it's like a bolt on a nut or something, and you want very high quality. Then for your internal thread, you go with class 4H. And if the same for external one, of course, this is fine. And depending on what you use, in the case that we did, we use class G, right? So if you want to go with class G and fine, and it's a short, you see there is nothing literally. But if it was a normal, you go with 4G. So in this case, if you want to go with the normal of both, we probably go with this combination. Okay? If not, then you can probably use the closest one to it. And you can use any combination of these, okay? You can use any combination. Many times, people use similar things, but you don't have to. So this could be 4, that could be 6 or anything. So here you can see different classes and different groups that are suggested based on the length of the thread engagement and the quality that you desire. So hopefully that helps. The last thing we want to talk about is, what if the thread is not metric? What if it's a UN or UTS, unified basically thread system? What about that? For those threads, we have 2 letters, 2 characters. One is a number, one is a letter. The class is basically that quality, which is like fine, medium, coarse. And the letter determines whether it's an external or internal thread. If you see letter A with it, that means it's an external thread. If you see letter B with it, that's an internal thread. So a 1/4 inch, 20 thread per inch. So this is your D. This is basically 1/P. UNC, unified coarse thread. And then what? So this determines the type of the pitch actually. And then class 2, which is medium quality, and it's an external one, it's A. Now, let's talk about these classes. How many classes are there? Actually, there are 5 classes in UTS, but 3 of them are in common use. 2 of them are kind of not being used commonly. So out of these 5 classes, what are these? Class 1 is the tolerance that is loose. So that is corresponding to a class like 8 or 9 in metric, okay? And this is where you intend to use the thread anywhere, even where the internal threads could be dirty or the external ones could be dirty. So you want to be able to put the thread, the bolt through the nuts in all conditions. So you use class 1. Now, if you want to be able to use it in most common cases, but maximize the strength, then what does it mean by strength? Because the coarse tolerance means there is going to be more backlash and space between the teeth. And when there is more space between the male one and the female one, over time, these two will start hitting each other, and then will be fatigue. And of course, it is going to break sooner. But if there is a small gap between them, the fatigue is going to be smaller, the load is going to be smaller on them, and they are not going to break that fast. So mid-class, something like 5-6 is class 2 for corresponding to metric. And then if you want medium high quality work, you go for class 3. Okay. Now, what is class 4? Class 4 is kind of a theoretical class that overlaps with 3, and that is obsolete now. So you barely ever see anything like class 4 in UNC or a UN system. Class 5 is a special class that the threads interfere. So you have to use a wrench and some good amount of torque to put them together. And that means the connections are permanent or semi-permanent. So here there will be interference. The threads will have interference. One is probably cutting through the other one. Okay, and you have to use a wrench and a lot of torque to do it. So typically, if we don't want to do that, for most scenarios, we use one of the classes 1, 2, or 3. Okay, hopefully this video was useful to you. This is a very important topic if you want to put tolerances on the threads. So thank you so much for your attention. I'll see you in the next video.